holding it in the sun maybe as a kid, focusing light down to that tiny bright point.
Oh, yeah. Feels almost like magic, doesn't it? Taking all that spread out sunlight and just concentrating its power.
Exactly. And that simple act, well, that bending of light, that's really the absolute core principle behind harnessing solar energy on a massive scale.
It really is. It's the foundation.
So in this deep dive, we're digging into material from light concentration for solar energy. Our mission really is to unpack how that fundamental idea scales up, how it powers these sophisticated solar systems.
Right. We're pulling out the key insights from the source material, the how, the why, the engineering challenges too.
Yeah, trying to give you a bit of a shortcut to understanding this pretty vital technology.
We'll follow the light's journey, basically, through lenses, see how concentration works in practice, and then look at the real-world applications for generating power from the sun.
Okay, so where does the source begin? It starts right there with that humble magnifying glass, describing it as, a standard convex lens.
Thicker in the center, thinner at the edges. That shape is crucial.
And the physics. The source points to refraction. Right?
Yes, refraction. That's the essential bit. Light bends when it goes from one thing to another, like air into the glass. It slows down, then speeds up again, going back into the air.
And the source highlights that the shape, that convex curve, it's specifically engineered for this, to make parallel rays of light, like the ones from the sun because it's so far away, converge.
Exactly. Instead of just passing straight through, the lens forces them together.
And the source identifies this critical point, the focal point, capital F, P, that specific spot where those parallel rays meet up.
And the distance from the lens center to that point, that's the focal length, little F key parameters.
What's fascinating here, and it really ties back to that childhood thing, is the source's insight that at this focal point, all the light energy that hit the whole lens
right, spread across that whole area.
gets crammed into this tiny, tiny spot.
And that's where the power comes from. The source really emphasizes this dramatic increase in intensity. It's not just, visual brightness. It's a significant jump in thermal energy, heat.
All concentrated right there.
Yeah.
That's why, as the source notes, you can actually use a magnifying glass to start a fire. You're focusing the sun's energy density onto something flammable.
It works. The source does briefly mention that these lenses also form images, real or virtual images, like when you use it to read small print.
Right, the magnifier effect.
But for solar energy concentration, the source material really zeroes in on leveraging that convergence, that focusing strictly for energy.
Okay, so that's one lens. Powerful in its own right.
Yeah.
But to get the kind of intensity needed for serious power generation, you probably need more, right? What does the source say about using multiple lenses?
It does. It shows how arranging multiple lenses in a series creates what's called a compound system. And this kind of system, well, it can achieve a much, much greater concentration of light than just one lens could ever do. You're essentially layering the effect.
So the first lens starts bending the light.
It starts the convergence. And then the next lens, or lenses, refine it even further, squeezing that beam of light down to an even smaller, more intense spot.
Pushing that concentration factor way up. The source kind of touches on this idea, the relay concept, where one lens's image is like the object for the next one.
Yeah, like in telescopes or microscopes. It hints at the complexity you can build into these optical systems.
And the whole setup, this series of lenses, it has an overall effective focal length, doesn't it?
That's right. And that effective focal length determines the final convergence point and, crucially, the degree of concentration you actually get.
But as always, there's a catch. The source is quick to point out that adding complexity, stacking lenses, isn't free. What sort of engineering challenges pop up?
Well, a major hurdle the source discusses is optical aberrations, things that mess with the perfect focus.
Okay, like what?
First, there's chromatic aberration. Basically, different colors or wavelengths of light bend slightly differently as they pass through the glass.
So they don't all meet at the exact same focal point.
Exactly. You get this sort of color fringing around the focus spot. The source does mention solutions, like using special achromatic lenses made from different types of glass bonded together. They help correct for that color spread.
I think I've seen that effect sometimes. Okay, what else?
Another big one is spherical aberration. If you use a simple lens with perfectly spherical surfaces, the light rays hitting the edges of the lens don't focus at the exact same spot as the rays going through the center.
So it blurs the focus, diffuses the energy a bit.
Pretty much. It makes the concentrated spot less sharp, less intense. The source notes that using aspheric lenses with non-spherical curves or clever combinations of lenses can help reduce this significantly.
Makes sense. And the source also points out something maybe less obvious, light loss. That becomes a bigger deal with multiple lenses.
Yes, absolutely. Every single time light hits a surface, like going from air into glass or glass back into air, a small amount gets reflected away and a little gets absorbed by the glass itself.
And with multiple lenses, you have lots of surfaces.
Right. Air glass, glass air, air glass again. These small losses add up. They accumulate through the system. The source really highlights that anti-reflective coatings on every lens surface are vital. Essential, really, to maximize the amount of light that actually makes it through to the final concentration point.
So these aren't just minor optical issues. The source frames them as real efficiency barriers. Things engineers have to actively solve for solar concentration to work well.
Definitely. They're practical engineering problems.
Okay, so we have this power of concentration. We understand the challenges of scaling it up. Where does the source show this actually being applied in solar energy generation?
It really focuses on two main technologies that use this principle. Both aim to increase the sunlight intensity, maybe hundreds or even thousands of times, making it potent enough for power conversion.
Right. And the first application discussed is concentrated solar power, or CSP. How does the source say that works?
So CSP systems use lenses, or interestingly, sometimes mirrors, which can also focus light through reflection to concentrate sunlight onto our receiver.
A target, basically.
Yeah, a target. And this incredibly intense, focused light heats up a fluid in that receiver. The source mentions things like water, special oils, or even molten salt getting heated to very, very high temperatures.
And it's that intense heat that does the work.
That's the idea. The superheated fluid is then used to create steam, just like in a conventional power plant. That steam drives a turbine, the turbine spins a generator, and you get electricity.
So it's like a traditional thermal power plant, but the heat source is focused sunlight instead of, say, coal or gas.
Precisely. But the source makes a crucial point here about scale. For utility-scale CSP, you can't just use enormous versions of a standard magnifying glass. They'd be incredibly thick, heavy, and way too expensive.
Ah, okay. So what's the innovation the source highlights to get around that practical problem?
Fresnel lenses. Fresnel. These are pretty ingenious.
How do they work?
Instead of a single, thick, smoothly curved piece of glass, a Fresnel lens uses a series of concentric rings, like grooves, etched onto a much thinner sheet of material, often plastic.
Okay.
Each ring section has the precise angle needed to bend light towards the focal point, just like a section of a thicker lens would. So it mimics the optical effect of a big, curved lens, but with far less material, making it lighter and cheaper. The source mentions different types, like linear ones that focus light onto a pipe or point-focus ones.
Clever. Okay, so CSP uses concentrated light to make heat. What about the second application, concentrated photovoltaics, or CPV?
Right, CPV takes a different approach. It also uses lenses to concentrate sunlight, but instead of heating a fluid, it shines that intense light directly onto small, specialized solar cells, photovoltaic cells.
The kind that make electricity directly from light.
Exactly. So the focused light directly generates electricity within those cells.
What are the advantages of doing it that way, according to the source?
Well, a key insight the source points out is cost savings on the cells themselves. Because the light is so concentrated, you need much, much less of the expensive, high-efficiency solar cell material. A tiny chip receives light equivalent to maybe hundreds or even thousands of suns.
So you trade cheaper lenses for expensive cell area.
Sort of, yeah. And the source also notes another potential benefit. Some types of high-performance solar cells actually become more efficient when they operate under this intense, concentrated light. Up to a point, anyway.
Interesting. And the source says these systems often use arrays of smaller lenses, maybe Fresnel lenses again.
Often, yes. Arrays of smaller lenses, each focusing light onto its own tiny high-efficiency cell.
But concentrating all that sunlight onto a small cell must generate a lot of heat, right?
Ah, you've hit on CPV's major engineering challenge, which the source really emphasizes, thermal management. All that concentrated light dumps a ton of heat directly onto those sensitive solar cells.
And heat is bad for solar cells, isn't it? It reduces their performance and lifespan.
Exactly right. Excessive heat kills efficiency and can degrade the cells permanently over time. So the source stresses that effective cooling systems, whether they're passive, like heat sinks, or active, maybe using fans or fluids, are absolutely critical for CPV. It's a constant battle to dissipate that heat and keep the cells operating well.
Makes sense. And is there anything else the source points out that's essential for both CSP and CPV to work efficiently?
Yes. One absolutely crucial requirement for both, especially for high concentration systems: precise solar tracking.
Following the sun across the sky.
Continuously. To keep that incredibly focused spot of light perfectly aligned with the small receiver in CSP or the tiny cell in CPV as the sun moves, the entire system has to track its path accurately. The source mentions dual-axis tracking following both the sun's east-west path and its up-down elevation is often needed to maximize energy capture, especially when you're concentrating the light so much.
Okay. So stepping back a bit, the source lays out these powerful applications, CSP and CPV. But what are the big picture practical challenges in actually deploying these systems effectively?
Well, beyond that specific thermal issue in CPV we just discussed, the source summarizes several key hurdles that apply broadly. First, just maintaining that optical efficiency, minimizing all those little losses from reflection, absorption, and those aberrations we talked about earlier. Every percentage point matters.
And then there's the cost and complexity of manufacturing them in the first place.
Definitely. These aren't simple systems. They require precision optics, mirrors, or lenses made to tight tolerances. And the materials themselves have to be incredibly durable. Think about it. They need to survive outdoors for 20, 30 years under intense sunlight, wind, rain, temperature swings.
Yeah, that's a tough environment.
Then there's that ongoing operational challenge of thermal management, making sure components don't overheat and degrade. And something surprisingly mundane but critical: maintenance, keeping those lens or mirror surfaces clean. Dust, dirt, bird droppings, anything that blocks light significantly reduces the concentration and the power output.
Right. So bringing it all back to where we started, that simple magnifying glass image, this deep dive into the source material really shows how that fundamental principle of bending light gets built upon layer of physics and engineering to create these complex, powerful technologies like CSP and CPV.
Yeah, we've tried to pull out the essential insights from the material, how concentration actually works, the different types of lenses like Fresnel's, the key ways it's applied, and also acknowledging those very real engineering challenges that need to be overcome.
And it seems despite those challenges, the source suggests that ongoing advancements are definitely making these solar concentration technologies a really vital and growing part of our renewable energy future.
Absolutely.
Yeah.
So maybe here's something to think about. This fundamental principle, using lenses or optics to manipulate light, to concentrate energy or even information, that obviously goes way beyond just solar power. Consider where else in your life, maybe in technologies you use every day, this basic idea of controlling light might be quietly at work, or where perhaps future innovations based on this same principle could pop up in completely unexpected areas.